Okay, we made it to Friday. Today we're going to be doing lesson 8, which is linear versus exponential. This is a pretty important concept. It's pretty simple. We're basically just going to be comparing linear equations and functions and exponential equations and functions. You will be using your calculator a little bit, so make sure you have it ready to go. This page number I think is the right page number for the homework. If I'm wrong, just post it on the comments for everybody. All right, let's get started. Okay guys, so today for this lesson, I printed out the PDF of the lesson instead of the entire lesson because I did skip over a question or two to try to make it a little more straightforward. So linear and exponential functions share some characteristics, and that's because they're based on two different but similar sets of principles. The first is that a linear function is based on repeatedly adding the same amount. That's your slope, right? So your rate of change is constantly increasing or decreasing at the same rate. Exponential functions are based on repeatedly multiplying the same amount. So that would be your base in your function. You're either multiplying by a whole number or multiplying by a fraction, right? So in exercise 1, we're looking at two tables here, and one of them represents a linear function and the other one represents exponential. So our job is to decide which one is which and explain how you arrived at your answer. So make sure you don't jump to conclusions here. Make sure you look carefully, because from the first to the second, I could say here that I'm adding 5, but you must check the second to the third, because if this was a linear function, I would be adding 5 again, right? However, what I'm really doing from 5 to 10 here is I am multiplying by 2. From 10 to 20, multiplying by 2. 20 to 40, and 40 to 80. So would this be my linear or exponential? If we're multiplying by the same number and over again, that would be exponential. Okay. In table 2, we're obviously not going to multiply anything by 8 to get 11. What would we add 8 to get 11? 3. And 11 plus 3 is 14. And 14 plus 3 is 17. And 17 plus 3 is 20. And this would be our linear function. Okay? You're supposed to also explain how you got your answer. So for the exponential one, every time x increases by 1, y is increasing by a constant factor of 2 each time. So x is increasing by 1, y is increasing by a factor of 2. And in the linear function, every time x increases by 1, the y value is increasing by 3 each time. Okay? In each case, the idea is that even though one is being added and the other one is being multiplied, they're both constant. Well, that's an important thing to remember. So for exercise 2, they want us to write the equations for these two tables. I'm not entirely sure why I split these up, but I'm going to keep it up here so that we can look back to it. For table 1, we know it's an exponential function, so we know that the format, so to speak, of an exponential function is y is equal to a times b to the x, right? And a is your starting point, or your y-intercept, and b is your factor. So a, my starting point, if you look back at your table, your y-intercept, remember, is where x is 0, so our starting point or our y-intercept for this function is 5. So a is 5. And b, our factor, we figured it out already, we're multiplying every time by 2. So b is 2. All right, so now what we're going to do is we're going to write this equation. This is y equals a is 5, so it's 5 times b, which is 2, to the x power. Y is equal to 5 times 2 to the x power. Guys, please remember, I know it's tempting to see the 5 times 2 here and say 10 to the x power. Why can I not do that? the 2 is raised to the exponent. So because x is in the exponent, we don't know what it is. We have to leave it like that. We can't combine 5 and 2 before we raise the 2 to the power of x. So it has to stay like this. This is not equivalent to 10 to the power of x. This is the simplest way that we can write this right now. Okay? All right, now let's go to the second table and write the equation for this one. This is a linear equation, function. So we are going to use y equals mx plus b. Okay, so m is our slope and b is our y-intercept. Okay, our y-intercept, as you can see, it's where we start. Remember, b is where you begin. And the y-intercept is always where x is 0. So that's 8. So our y-intercept, or our b, is 8. Okay? And our slope, we already know what it is. We already figured this out. And the only reason why by the way, we don't have to do y2 minus y1 over x2 minus x1 is only because x is only increasing by 1 each time. So when we do 11 minus 8 over 1 minus 0, it's just 11 minus 8 because 3 over 1 is still 3. Same thing here. 14 minus 11 is 3 over 1 is 3. Okay? So the slope is 3, or the rate of change. Okay? So to write this, it would be y equals 3x plus 8. And that would be our equation for the second table. Okay, so these are two equations for those two tables. They both have a constant rate. One of those, the rate of change does not stay the same, but the rate by which they are increasing stays the same. So I'm going to skip over exercise 3 for today. It's just a little bit something extra to show you that a linear function and an exponential function both can be determined, their equations can be determined by 2 points. So we looked in our Unit 4 fun that we did. We had 2 points, we found the slope, and then we went back and we found the y-intercept, and then we were able to write the equation. So the same thing actually goes for an exponential function. You can find the equation for an exponential function when you know 2 points. So it's not super important for right now, but it's kind of like one of those exploratory questions. So for now, we're going to skip over it because I want you guys to get just the basic gist of this right now. You can absolutely try it out, but we're gonna go forward with exercise 4. So this table is showing the exponential function 4 times 2 to the x power. And they're saying it's shown partially in the table. Of course, it's not the entire thing. They want us to find the rate of change over the various intervals that are given. Okay, so just like the previous table, the x is changing by 1 each time. So when we find these rate of changes, it's really only going to be the difference in the y's. The point of this is to show you how the rate of change in an exponential function is different, even though the factor stays the same, okay? So from 0 to 1, this is from here to here, okay? From 0 to 1, they want us to find the rate of change. Right now, remember, the rate of change is really f of b minus f of a over b minus a. But to avoid confusion, we're still using the slope formula because they are ultimately the same thing for now. But this is really f of b minus f of a over b minus a, remember? Okay, so this would be 8 minus 4. Sorry, I'm trying to hold my this at the same time. 8 minus 4 over 1 minus 0, which is really just 4 over 1, which is 4, okay? Now we're going to look from 1 to 2, where x is 1 to 2. So we're going to look at 16 and 8 here. 16 minus 8 over 2 minus 1. And that's 8 over 1, which is 8. Okay? Now from 2 to 3, we're looking at these. So we're looking at 32 and 16. So the rate of change would be 32 minus 16 over 3 minus 2, which is 16 over 1, which is 16. And finally, from 3 to 4, we're looking at 64 minus 32 over 4 minus 3, which gives us 32 over 1, or 32. So, what is clearly happening to the average rate of change as x gets larger? It's also getting larger, right? So, it's increasing. In an exponential function, the rate of change does not stay the same, right? That's what makes it different than a linear function. If it was linear, this would be 4 every single time, right? Since it's exponential, it's changing, but it's changing by a set factor, right? So what is happening each time? We're multiplying that rate of change by 2, right? 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. Okay? So here what we can write is the average rate of change is increasing as x is increasing. I'm going to abbreviate. The average rate of change is increasing as x gets larger. Okay, so anytime that our base or our factor is a growth factor, in other words, anytime it's bigger than 1, this is what's going to happen. We're going to get an increasing rate of change. So, on the other hand, if this is a number less than 1 or a decay factor, and it's decreasing, then the rate of change is going to be going down each time. All right? Simple enough, right? So the fact that the slope of an increasing exponential is always increasing has an interesting consequence. So we're going to look at exercise 5, and we're going to look at this first, the linear function y equals 20x plus 5, and then we're going to look at the exponential function y equals 5 times 2x. Notice that they both have the same y-intercept, right? Y-intercept in a linear function is here, b, that's 5. And the y-intercept in an exponential function is here, which is also 5. Okay? So, it says it right here. Both of the functions have a y-intercept of 5, so they both start in the same spot. So we're going to compare how they increase. So notice it says using your calculator, we're going to sketch these two curves. Remember, sketch means you don't have to be exact. And we're going to use the indicated window. Now, when I say the indicated window, look at the graph and look, on the y-axis, we're going from 0 to 30, okay? You could even go from 5 to 30 if you want. And the x values are going from 0 to 3. So in your calculators, we're gonna start off, clear this out from yesterday, okay? We're gonna start off putting in this function, 20x plus 5, 20x plus 5. Okay, and I'm going to adjust my window before I start. So my x min is going to be 0 and my x max is 3. Okay, so instead of 20, that's going to be 3. I'm leaving my scales alone. My y min, we'll look at it from 5 since it says 5, and the max would be 30. Okay, so push graph. And we have a nice straight line. Okay, so I should have adjusted that. The only reason the 5, I just realized the only reason the 5 is written on there is because that's where our y-intercept is. So let's change the min to 0 and see if we can just see it nicer. There we go, that's better. Okay, so because the y-intercept is 5, that's where our line is crossing the y-axis. So it looks like this. So you're gonna draw a line like this, and it's a sketch, so this is fine. Okay, sorry about that. Now what we're gonna do is we're going to graph the same exponential function here with the same window, okay? So go back to y equals, and you can even put them both in at the same time. You just have to push the down arrow, and we're gonna enter in 5 times 2 to the x power. So 5, use your parentheses, times 2, and then remember to do the x power, you push the caret button here, and you enter your x. Okay, hit graph, and now we can see both of them at the same time at this window. So what does it appear like from this window? Something like that. Sorry that my lines are so terrible today. Okay, something like that. Now the idea is that this is not how it's going to stay. The exponential function increases so fast that when we increase our window and make it go all the way up to 150, we can see what actually happens as y gets larger. So we're going to do the same exact thing. We don't have to change our y equals. We're only going to change the window. So we're going to change our y max to 150 and our x max to 6. Okay, so we don't have to change anything in y equals. We're just going to go to the window, and we're changing our x max to 6, right? And our y max to 150 so that we can see what's really happening here. And let's see what happens. There's our straight linear function again. Now here comes the exponential function. Whoa! Now all of a sudden it's surpassed the linear function, right? So in the previous graph, it looked like the exponential function wasn't going to catch up to that linear function. But as soon as you increase the window, before we were only looking to like about here. Now when you increase your y window there, you can see that the exponential function increases so quickly that it will always, always, always catch up to the linear function. So we'll just sketch this again. The linear function stays constant the whole time. The exponential function appears like it's not, and then whee, there it goes. And it eventually catches up, okay? Now we were supposed to label these, and I didn't do that before, so let's do that now. The straight one was 20x plus 5, and our exponential one was 5 times 2 to the x. Okay, and label these ones as well. Okay, and 20x plus 5. Okay, and those are our graphs. Now, although the line appears to rise more quickly than the exponential at first, the exponential eventually catches up and surpasses the linear. Why will an increasing exponential function always catch up with an increasing linear function? Well, the average rate of change in a linear function is constant, okay? So it's always going to rise the exact same rate no matter what. Nothing's going to interfere with that. On the other hand, the rate of change of the exponential function is always getting larger. Always, always, always. It's never going to stop getting larger. So eventually its rate is going to get larger than the linear's at some point. Even if the linear function has a really large rate of change, eventually the exponential will catch up, okay? So that would be, you can write that in your own words there, okay? And that's everything for today. So your homework / practice, Fluency 1 and 2, I said it in the post, but Fluency has a whole bunch of parts. It's really important that you're able to do that. There's a bunch of tables, and you have to figure out if they are linear or exponential and then write the equation. So it seems like a lot, but it's actually really easy stuff. Number 2 is a multiple choice one, and then applications 3, don't look at it and get overwhelmed just because it's a word problem. It's actually pretty easy. And Anthony and John on the Regents, they usually give you a question. It's typically a part 3 question, where they will ask you to look at a table or some kind of function that's described in words, and they'll ask you what type of function would be best modeled, would best model this situation, and you have to decide if it would be linear or exponential. Okay, that might even be a part 2 question. I can't remember, but it's very, very common, and so this type of practice is great for you guys. Now, before I let you go, just a few things quickly. I need to remind you guys that you need to be reading the daily agenda every single day. I know it looks like a lot of reading, but I have everything that you need to know there. Everything is listed. Some of it's the same every day, but there's other things that I'm adding in there daily. So I need you guys to really make sure you're reading those every day. Also, the posts on Google Classroom, you have to, when I have these assignments up there, you have to click turn in. Now, I'm not seeing it from the student view, so I can't see where that button is. So if you need help finding that, I suggest that you ask one of your friends to help you out, because some people are turning it in and other people are not. So when I go to grade it, it's telling me that you haven't finished it yet, and it's kind of messing up the whole process. So please make sure you're actually turning in the opening tasks and the homework, okay? You guys have been doing a great job overall. Also, one last thing, if you can't upload a picture of your homework on Google Classroom, it might be because there's so many people using it right now. So when in doubt, if it's just not loading or something, you can always just email it to me. All right, guys, so as always, any questions, just put a comment on Google Classroom and I will do my best to get it answered for you. Okay, guys, have fun and have a good weekend.